This is NMR problem 8 from Blackboard.
Warning. Warning.
Spock, what is it? Captain, long-range sensors have picked up an unknown compound. And here's our unknown compound, C4H7Br02. We're first going to find out the degree of unsaturation, and when we do that, we're going to use the formula degree of unsaturation is equal to 1 plus the number of carbons minus 1/2 the number of H, which represents both hydrogens and halogens, plus 1/2 N. And when we do that, it's 1 plus 4 minus 1/2 of 8. That's 7 hydrogens plus 1 halogen, and that gives us 1 degree of unsaturation. That tells us that we have either a pi bond or a ring. And the next thing we're going to do is talk about IR. If you haven't already, you can go to premed411.com. On the home page, click on Easy Notes and download IR Review. You need to know panels 1 through 5, and one of those panels is for a carboxylic acid, and it looks like this. We see a very strong broad absorption from 3400 to 2400, and we see a 1700 absorption, which is strong, indicating the carbonyl, and then this is the hydroxyl group of a carboxylic acid. If we look at the IR for our compound, we see that this matches up with what we expect. Here we have a strong and very broad absorption, and that extends from here to here, which turns out to be 3400 to 2400, but usually it's going to go somewhere peaking in the middle of about 3000. That's an easy way to spot it. And then right over here it's going to be our carbonyl. So we know for sure that we have a carboxylic acid. Our next step is to look at the proton NMR. So here comes the proton NMR. We see here a signal by 12, and that is going to be the proton of the carboxylic acid itself. And it comes in between 10.5 and 12. Carboxylic acids are the only thing you're likely to see here. It's almost certain to confirm what the IR told us. Now we have 4 carbons, and so 2 carbons are accounted for, and we have to take a look at the other 2 carbons, either a straight chain or branching like this. If we look here, we see a singlet. Now singlets are great. They make it easier to determine the structure of the compound. We know that this here is 1 hydrogen, and if this is 1 hydrogen, then over here this must be 6 hydrogens, because there's only 7 hydrogens total in the compound. And a 6 hydrogen singlet is the signature of 2 methyl groups, 2 CH3s. Now if you think about that, that makes it pretty clear what the structure must be, because there's only one way to get 2 methyl groups, and that would be like this. What you would have is a 1 hydrogen singlet way over downfield around 12, and then you'd have a 6 hydrogen singlet much further upfield. Now let's say that didn't occur to you. If that didn't occur to you, you can brute force it, and on a multiple choice test that means that you can work through the possibilities that are listed. And so some of the possibilities would be straight chains. This would be one possibility here, but clearly this will have more than just 2 signals. It'll have 4, 1, 2, 3, and 4, and it will have splitting. So that's not correct. You could also have a structure that's going to look like this. That would also give you a total of 4 signals and splitting. So you could say, well, that can't be correct either. Well, what's going to be left? Well, at this point, you'd have to have a carbon structure like this, and you could either put the bromine here, and if you work that out, you're going to get splitting and 4 signals. Or what you could do is you could put the bromine, well, that won't overlap, so we'll put it here. You could put the bromine in the center, and that works out great. Next step, let's take a look at the carbon-13 to see if it matches up with what we think we have. And there's the carbon-13. What do we see? We see that right over here we're going to have 2 carbons that should appear the most upfield, and that's because they're furthest from the electron withdrawing carbonyl and the Br. This pointing up like this indicates that it's consistent with a CH3 group, and these 2 signals here, those don't show anything up over here where we have splitting. That means that they contain no hydrogens. Those don't show up. That's consistent with the fact that these have no hydrogens. Furthermore, the carbon that we see here, the carbonyl, should be around 200, just pretty far downfield, and we see that as well. So that kind of works out. We're very happy. Last thing, not a big point, is going back to the proton NMR here. There's a mention here that this hydrogen exchanges with D2O. What that means is if we put this carboxylic acid into deuterated water, and deuterium is an isotope of hydrogen, what ends up happening is, because of the large excess of deuterium, this hydrogen comes off and deuterium comes on. And deuterium is invisible in the NMR, so this signal disappears when we put it into deuterated water. Not a big deal. That's true for all the protic hydrogens. Hydrogens on oxygen are protic, and that's how that works. Another successful IR NMR problem.